Okay, let's do number 64 minimum path sum on LeetCode. Um, so let's get to what the problem's asking. The problem's asking, given an m by n matrix, find the shortest path from the very first number in the matrix to the very last number in the matrix. So in this example that they've given us, this is our m by n matrix, and we are going to find the shortest path from this one to this one. And as we go down any of our paths, we will take the sum of all the values in our path. Keep in mind that when we go through our matrix, we can only go two directions. We can either go down or right. So let's look here. If we start at 1 and we decide to go down, and we find the sum of the path that we're going down. We're starting at 1 here. If we go down, then 1 plus 1 is 2. So now we have 2. When we go down again, we find a 4. So 4 plus the 2 that we just went by, 1 plus 4, that's 6. So we're at 6 now. Then we go right, 6 plus 2, that's 8. And 8 plus 1, that's 9. So if we take this path right here, then we get the sum of this entire path. As we said earlier, that would be 1 plus 1 plus 4 plus 2 plus 1. Which is 9. Alright, so let's look at another path. Let's say instead of going down first, we decide to go right first. So let's find the sum of this path down here. So if we go right first, we start with 1. Then as we go right, 1 plus 3 is 4. We see another 1. 4 plus 1 is 5. Then we go down. 5 plus 1 is 6. 1 plus 6 is 7. So we could see that the path when we went right first, or the sum of the path when we went right first, is less than the sum of the path when we went down first. This means that the optimal path to go down in this given matrix would be this path right here. Okay, so now that we understand the objective of this problem, which is to find the shortest path in our matrix, I've created the matrix from the example and a temporary matrix. So what we're going to do is we're going to go through the matrix in big O of n time. And the way that we're going to do this is the standard nested for loop, where we go through the number of rows first, and then each individual column. So I've created a temporary matrix filled with pound signs. And keep in mind that when you create a matrix, or integer matrix in Java, it would be filled with zeros and not pound signs. So I just used pound signs for now because I thought it would be easier in terms of explanation. So what we're going to do is, as we go and iterate through every number in our matrix, we want to find the value of the path that we've traveled down by. So let's suppose I decide to go down this path right here, which is 1, 1, 4, 2. 1. What will happen is at our beginning, we'll start out with the value 1 because that's what we start out with. Let me just make this black. Okay. So then we move on to the next position on our path, which is down here. And we see that this value is 1. So we'll add it to the value of our current path, which is also 1. So 1 plus 1 is 2. And then we go down to the 4, which is this position right here. So what do? We say, all right, we have a 4, we have a 2, the sum of 4 and 2 is 6. And now we go down to this position. Then we say 2 plus 6 is 8. And finally, we'll go to our last position to complete the path. 1 plus 8 is 9. So notice that this 9 represents the sum of all of these numbers here in our path. 1 plus 1 plus 4 plus 2 plus 1 is 9, which is the sum of the path that we just took. And this is one path that we could take. Let's say instead we want to take this path right here in blue, which is 1, 3, 1, 1, 1. Alright, so let's take down the path. We'll go right first instead of going down. So we'll say 3 plus 1, is 4. Okay? 1, then we go right again. 1 plus 4 is 5. Okay. And then we go down. 1 plus 5 is 6. And now this is the important part. As we go down this path and we go to our last value, we will see that there's a bit of a clash between what two numbers should be in the last position. We have either 9, which is the value that's already there, or we could change it to the new value of this new path that we've taken, which would be what? 1 plus 6 is 7. So we say, hey, 7 is less than 9, so I'm going to keep 7 instead of 9. Let's erase that 9 and keep the 7. Alright, so let's say that this given matrix is called grid, which it is actually called grid in the problem. And the very first thing that we'll do is we'll add the sum of our path in every position. So as we did here, the 2, 6, 8, so on and so forth. So the first thing that we're going to check is if I is greater than 0 and j is greater than 0. If this holds to be true, then we will be in this yellow vicinity, because here, all these values here, j would be 0, and all these values here, I would be 0, right? So if we're in this yellow area, let's say we're in this pound sign right here, right? We're currently in this pound sign. Well, to have gone into this pound sign, we could have either have taken this path right here, or have taken this path right here, right? But we have to check what path. Let's say this is path 1 and this is path 2. We have to check what path is shorter, right? So the way we do that is we'll save the current path. So the way that we'll decide the shortest path between path 1 or path 2 is that we'll check the values before we got to this pound sign. So we will check, circled here in green, 2 and 4. And we will check to see which one is a lesser value. So the lesser value would obviously then give us the value of the shorter path in this position right here. How do we do that? Well, we could simply say something like that position right there, pound sign, because again we're in pound sign, would be math dot min and math.min returns the minimum value of two numbers that you throw at it. And then we'll just put 2 and 4 there. Sign's position is 1, 1. This one would then have to be 0, 1. And this one will then have to be 1, 0. So this means that we could then get g of I minus 1, right? G I minus 1 would give us this 4, and we'll keep the second one the same, would just be j, or g of the same I, but this time we'll say j minus 1. And then this would then give us the value of which path we should check 1 or 2, which would be the shortest one. In this situation, the shortest path would be 2, so this pound sign will turn into 5 plus 2, which is 7. So the last thing we want to check is we want to check whether we're traveling down by the first row or the first column, right? So here, if I is equal to 0, if I is bigger than 0, that we know that means that j would be 0. So here, j would be 0 in all of these. And here, if j is greater than 0, then we know that I would then have to be 0. So let's illustrate these three possibilities in different colors to make it more clear. We'll illustrate these three possibilities in different colors. So let's say that this region that we could potentially go down by, pink region, would be this scenario right here. This region right here in green would be going down these values. And finally, this region right here in yellow would be going down these values. So this is how we've partitioned our matrix into three possible scenarios. The last thing that we have to know is what happens when we go down, or what we do when we're in the yellow or green segments of the matrix. Okay, so once we're in the yellow or green region, all we have to do is add the previous number into our path. So suppose we're in this pound sign area, we just have to add the previous one, which would be this previous pound sign right here. Finish this problem and code the solution. So, as we said earlier, we want to create another matrix that we'll call G, and it would have the same number of rows and columns as our grid matrix. So new int grid.length grid 0.length. One more thing I didn't mention is that we want to create a small base case scenario, and this is essentially going to check if the grid is empty, so if it's equal to null, if the grid hasn't been initiated, or if the grid length is equal to 0. If that holds to be true, then we can simply just return 0. Okay, so now we're going to iterate through our entire matrix. Is equal to 0, I is less than G dot length, I plus plus, and then again here, or this would be J, and we'll go through Gi dot length. Okay, so now we're going through the entire matrix, and the very first thing we want to do, as we said earlier, is we want to add the positions of the value of the path at every position that we go to. So G, I, J, J is equal to plus 2 grid I, J. Now remember those three sections of the matrix that we talked about earlier, the rows, columns, and what's in between? We're going to create three case scenarios for those three. So the first one was if I is bigger than 0 and J is bigger than 0. We'll do something here. Else if I is bigger than 0, else if J is bigger than 0. Okay, so if I is equal to 0 and J is equal to 0, we have to get the minimum path from where we came from. So math.min dot min of gi minus 1 j and I j minus 1. Again, the math.min will give us the smaller value of what we pass it to, and this would be set to the current position at our new matrix. Okay. And as you can remember here, we just have to check the previous I. That's all we have to do. So the previous I, j, I, j. Finally here, we just have to check the previous j position. So it seems that I misspelled grid here, so it didn't run. Let's try this again. Yeah, finally we'll return the very last value in our new matrix, which is g dot length minus 1, g dot g0 dot length minus 1. Alright, let's submit.